By now your mains exams are already over. If you are scoring between 160 to 180, okay, directly start preparing for advance. Why I'm saying is that because in boards, especially for CBSE pattern, for those who are giving boards from CBSE boards, CBSE has focused more on numericals in recent years, okay, and the difficulty of questions, okay, are more or less has been increased. So if you start solving JEE questions for your boards, that will be very helpful instead of directly going for PYQ means PYQ of boards. The PYQ of boards is obviously going to be helpful, but you are going to optimize your selection for JEE, okay. So directly start practicing JEE advanced question on your boards type pattern. That means write out the detailed solution, draw the diagram, okay, write out the formulas and things. In advance, you do not need to do all those things, but you get 1 month to optimize that much thing for advance. Okay. So if you're starting with class 12, okay, start with class 12 of JEE advance, okay, electrostatics, current electricity, electromagnetic induction, modern physics, and those chapters, and solve the JEE advanced questions. Okay, and write down the everything as elaborate type of answer. Okay, to be very helpful for your both also. Understood? Because there is no use of studying different things for boards and different things for advance. Understood? Okay. Having said that, let's start with the question. Okay. And if you have any doubts regarding any questions or if you have any doubts regarding the explanation of what I've given you, do mention them in the comment section. Okay. So before starting with this question, let's discuss a certain topic called moment of inertia. Moment of inertia. Now, this moment of inertia is nothing but the equivalent of mass in rotational motion. Okay. And moment of inertia is always defined about the axis here and time. Now I'll give you certain moment of inertia of certain specific objects that are going to come in your exam. Okay. Moment of inertia of a ring, moment of inertia of a disc, moment of inertia of a sphere, moment of inertia of a rectangle. Because it is unwise to integrate everything when it comes. Okay. When it means as soon as the question comes. Because integration will already be done in your classes, no? I'll give you the certain specific and how to integrate them. Okay. So the thing that I'll discuss is moment of inertia of certain specific objects. And before discussing that, there are two theorems that you need to learn about moment of inertia. One is perpendicular axis theorem, and the second one is parallel axis theorem. Perpendicular axis theorem, and the second one is parallel axis theorem. Parallel axis theorem. Okay. Perpendicular axis theorem is valid only for 2D bodies or 3D bodies. Okay. Valid only for 2D bodies. So what perpendicular axis theorem says is that suppose there is a 2D shape. Okay, I'm taking a plane of paper. Okay, I'm taking this plane of paper. Okay, the plane of paper is in this plane. Okay, let's say any shape in this plane. Okay, I can draw any shape in this plane, not necessarily a rectangular shape, but the shape has to be in this plane, and the shape is 2D. That means there is no thickness of this plane. Okay, if the moment of inertia about any axis passing out here is Ixx. Okay, this is the plane. Moment of inertia about this axis is Ixx. Moment of inertia about this axis is Iyy. Iyy. Moment of inertia passing through this axis is some other Ixx. Moment of inertia passing through this axis is Iyy. Okay, and let's take another axis Z. Okay, Z is perpendicular to the plane. Z is perpendicular to the plane. Izz. The moment of inertia about this rectangular plane passing through Z axis is nothing but Izz. Okay, moment of inertia of this 2D object passing through the axis is Izz. Then perpendicular axis theorem states us that Izz or moment of inertia passing through the perpendicular axis is equals to moment of inertia passing through Ixx plus moment of inertia passing through Iyy. Okay, that means moment of inertia passing through this axis plus moment of inertia passing through this axis is equals to moment of inertia passing through this axis. This is our perpendicular axis theorem. And the second one thing that I'm going to discuss is parallel axis theorem. Okay, what parallel axis theorem states that and this is valid for any bodies. Okay, 2D bodies, 3D bodies, 4D bodies, any type of bodies. Okay, 1D bodies, 3D bodies. Okay, 3D bodies also include 1D bodies and 2D bodies. Okay, what this theorem says is that suppose there is any object. Okay, let's say this is my, or let's say this is my object. Okay, this is my 3D object. what perpendicular axis theorem, sorry, what parallel axis theorem says that suppose I have a moment of inertia passing through, or I have this axis. Okay, I have axis and the moment of inertia of this entire body passing through this axis is I. And this axis is passing through center of mass of the body. Okay, the axis necessarily has to pass through center of mass of the body. So moment of inertia about center. Okay. Now, if you know the value of moment of inertia about an axis that is passing through the center, you can find out any moment of inertia parallel to this axis. That means if I want to make my axis, a new axis out here. Okay, suppose this is a new axis, I have to find out the moment of inertia of the entire body about this new axis. Okay, so what parallel axis theorem says is that moment of inertia about new axis, okay, and the new axis must be parallel to the axis that is passing through the center of mass. Understood? That is why parallel axis theorem. So moment of inertia about the new axis is equals to moment of inertia about the old axis plus mass of the entire body, where m is the mass of the entire body, into distance, okay, or perpendicular distance between both the axes square, into perpendicular distance between both the axes square. So this was our perpendicular axis theorem, this was our parallel axis theorem. One more theorem that you can apply out here is principle of superposition. What principle of superposition is nothing but, suppose I have a body, okay, and I want to find out moment of inertia of this body. Okay. Now, suppose I don't know the moment of inertia of this entire body. Okay, but I do know the moment of inertia of this shape. Okay, this shape. This shape is nothing but half of this shape. That means this part is nothing but this part. And I know the moment of inertia of this part also. Okay. So what principle of superposition states that moment of inertia of the entire body is nothing but moment of inertia of this body plus moment of inertia of this body. The moment of inertia of the entire body is equal to moment of inertia of this body plus moment of inertia of this body. This theorem or principle of superposition can also be applied in reverse. What do I mean out here is that suppose I have an object. Okay, suppose I have a spade. Okay, and this spade is hollow out here. Okay, I need to find out the moment of inertia passing through this axis. So moment of inertia passing through this axis is nothing but moment of inertia passing through the entire sphere assuming this field minus moment of inertia passing throughout the hollow part. Okay, assuming this field. So this is nothing but our principle of superposition in the chapter of moment of inertia. Okay, so we are going to remember these three theorems or three parameters to find out moment of inertia. Principle of superposition. See, this theorem is not exactly called principle of superposition, but the numerical or the method by which we are applying is very similar to principle of superposition. That is why I have named it this one. Okay, principle of superposition. Superposition. That means you can add out shapes to find out the moment of inertia of the total shape. Okay. Now, what are the basic shapes that I'm going to discuss out here? Okay, I'll start with ring. Ring, then disc. Okay, then cylinder, hollow cylinder and filled out cylinder. 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 Then rod. After that, rectangular plate. Plate. Okay. After that, cube. Not exactly symmetric cube, but a rectangular cube. Rectangular cube. Okay. These moment of inertia are very common and will be repeatedly asked in your examinations. Okay. After that, hollow sphere. Okay. Hollow sphere is also known as shell, a spherical shell. Spherical shell. And filled out sphere is known as sphere, a spherical sphere. Spherical sphere. And there are certain things that are not that much common but can be asked. Okay, let's remove the thing. Let's draw a line out here. Yes, let's draw a certain line. Okay. Okay, let's draw this line and we'll draw out the moment of inertia of uncommon shapes. Uncommon shapes are nothing but cone. Okay, Then after that, after cone, hemisphere you can already do. See, if you know sphere and if you know this theorem, if you know the third theorem, you can already make out hemisphere, okay, quarter of a sphere, and those are things. Okay, so we'll discuss moment of inertia of these specific objects. Okay, then trapezoid, those kind of things. But those thing won't be important and those thing won't be marked asked. Okay, in trapezoid. Trapezoid. Okay. This portion won't be not won't be coming. See, it is inside your syllabus, but it is not frequently asked questions. Okay. These portion are frequently asked and they are repeated in manner. So I'll discuss them and then I'll move to this one. And then I'll solve out this question. So it is much easier for you to understand. Okay. Now the first discussion in our syllabus is ring. Okay. Ring. Suppose there is a ring. Okay, and the ring is in this plane. Yeah, that means ring is in this plane. The moment of inertia of the ring passing through the axis through the center of mass of the ring is nothing but I is equals to m into r square. Okay, and r is the radius of the ring and m is the mass of the total ring. Understood? Now the not ring, it is ring. I don't know why I put it there. Okay, I into m square. That is the moment of inertia passing through this center axis. Now the variation of this question is nothing but find out the moment of inertia about ring or of the ring about the sides. Okay, to find out the moment of inertia about the side. Suppose I'm drawing the same ring. Okay, mass m, radius r. To find out the moment of inertia about this side. Okay, I'll just use parallel axis theorem where moment of inertia about this axis is nothing but moment of inertia passing the center of mass of the ring m r square plus m into this much distance square or r square. Not this much distance, this much distance. The distance between new axis and old axis. The distance between new axis and old axis. So mr square, this is nothing but the moment of inertia passing through the center plus mass into distance between both the axis, or distance between or perpendicular distance between both the axis. Or moment of inertia passing through the side of the ring is nothing but 2 square. 2 square. Now the third variation of this question is this is a ring. Find out the moment of inertia. That means if this is the plane of the ring, find out the moment of inertia passing through in one of the axis that is in the plane of the ring. That means my ring is in this plane, my axis is also in this plane. Okay. So out here, what will happen is moment of inertia. See, I can use perpendicular axis theorem out here. Because if I draw another axis that is perpendicular to the new axis, okay, I can say this axis to be ix, I can say this axis to be iy. And by observation, I can say moment of inertia through ix is equals to moment of inertia through iy because of the symmetry of the body. See, a ring is circular, no? So suppose this is a ring. Okay, the moment of inertia about this axis is equals to moment of inertia about this axis because it is a ring and it is symmetric. Because if you rotate this axis out here, it will become this axis, no? See, for a ring, if you rotate this iy axis by 90 degrees, it will be ix axis, no? Isn't it? So by symmetry, by observation, by symmetry, we can say that iy is equals to ix. Symmetry, you can say that moment of inertia through y-axis is equals to moment of inertia through x-axis. Okay. Now I already know the moment of inertia through perpendicular axis or moment of inertia through iz axis. Iz. So I do know that iz is equals to ix plus iy, isn't it? Or iz is nothing but mr square and ix is equals to iy. So I can write 2 times ix or 2 times iy. It doesn't make a difference. Okay. Or moment of inertia part of the ring passing through the plane of the ring or the axis is passing through the plane of the ring is nothing but mr square by 2. Okay. There might be another variation of the question. If this axis that is passing through the plane of the ring is touching one of the surface of the ring, okay, then again you apply this parallel axis theorem. This ix, the ix out here or the iy out here is passing through the center of mass of the ring. No? Okay. If you apply similar parallel axis theorem, okay, and to find out the moment of inertia passing through this axis that is with the plane of the ring. Okay, I. So moment of inertia of the new axis is equals to moment of inertia passing through center of mass plus moment of inertia, sorry, not moment of inertia, plus mass of the ring and perpendicular distance between both the axes. That is perpendicular distance between this axis and the axis that is passing through center of mass. Okay, this is nothing but mr square. So I is equals to half mr square plus 1 mr square. This is nothing but 3 by 2 mr square. So these are all the variations for the ring. Okay. Now the second part of the thing that we are going to discuss is disk, okay, or a 2D disk, or a 2D circular disk. So difference between disk and ring is nothing but the disk, the entire plane of the disk is covered with mass. In ring, the entire center of the ring is hollow. Okay, we have to find out the moment of inertia about perpendicular axis passing through the center of mass of a disk. Okay, so let's start with the derivation, then we'll go. Acha. The disk is kept in this plane. Suppose I am seeing the disk like this. Okay, I'm seeing the disk like this. So when I'm seeing the disk like this, okay, this is nothing but this is the axis, isn't it? This is the axis. Okay. Now the mass of the disk is m, the radius of the disk is r. How do I find out moment of inertia? We know that moment of inertia of the ring is nothing but mr square. And we also know that this can be made out of elemental rings. That means if we integrate out elemental rings, okay, from 0 to radius r, we get the moment of inertia of this, isn't it? So suppose let the mass of this ring be dm. Okay, mass of this much amount of ring is dm. And radius of the ring, radius of this white ring from the center is nothing but smaller. This is smaller. Okay, the moment of inertia of this small elemental ring or small elemental white ring is nothing but di is equals to dm into small r square. Now somehow I have to integrate this small ring from 0 radius to radius is equals to capital R, isn't it? What is the relation between, how do I integrate ring to form a disk? I have to find out the area of the ring. Okay, let the thickness of the ring be dr. The thickness of the ring is dr. So the area of ring is nothing but 2 pi r dr. Okay, always remember area of a ring is nothing but 2 pi r or perimeter of the ring into thickness. Okay, area of the ring is nothing but perimeter of the ring into thickness of the ring. Okay, suppose I have certain ring. Area of this ring is nothing but radius of the ring into thickness. Okay, and the inner radius or outer radius, it doesn't matter because the thickness is very small. The inner radius is equals to outer radius. Okay, so perimeter of, not perimeter, area of a ring is nothing but 2 pi r, perimeter of the ring into thickness of the ring. Okay, and mass m. Mass m was the mass of the entire disk. No? So what is mass of the ring? So you know that density of the entire disk is same. So density is equals to mass by area or planar density. I'm not talking about volumetric density. I'm talking about planar density. Mass by pi r square, which is equals to mass of the ring or the density of the entire disk is equals to density of this ring because both are made up of same material, isn't it? Is equals to density of ring or mass of ring divided by area of ring, 2 pi r dr. Okay, now using these two equation I can get that pi and pi will get cancelled. Okay, dm is equals to m by r square into 2r dr, isn't it? This is the mass of the ring. Now if I apply this elemental mass, okay, so elemental is nothing but dm. Dm is nothing but m by r square into 2r dr. This is nothing but the dm. This is nothing but dm that I have written out here into r square into r square, and I have to integrate this from 0 to capital R. So total moment of inertia is nothing but m by r square into 2 into r cube dr. Okay, integration of r cube dr is nothing but r to the power 4 by 4 or r to the power 4 by 4. The limits of integration are from 0 to capital R. Okay, so moment of inertia is nothing but m by r square into 2 into r to the power 4 minus 0 to the power 4 by 4, which is nothing but r to the power 4 by 4. So if I cancel it out, moment of inertia of a disk is nothing but m r square by 2. Okay, so moment of inertia of a disk passing through the center perpendicular to its plane is nothing but m r square by 2. So I is equals to mr square by 2. Now the same variation, what is the moment of inertia passing through side? You have to apply parallel axis theorem. Okay, so if this is the same disk, okay, I have to find out the moment of inertia passing through sides. The moment of inertia passing through side is nothing but moment of inertia passing through center of mass plus mass of the entire disk into distance square, distance between or perpendicular distance between both the axes. Okay, perpendicular distance between center axis and perpendicular means and the axis that I have to find out. So moment of inertia passing through side is nothing but 3 by 2 m square. Okay, where m is the mass of the disk. Okay, Now the another variation of this question: what is the moment of inertia passing through the plane of the disk? Simple out here again, I can apply perpendicular axis theorem. By observation, you can say that moment of inertia passing through x is equals to moment of inertia passing through y. Okay, so Iz is equals to Ix plus Iy. By observation, we can say that Ix is equals to Iy. So 2Ix. And we know the value of Iz. The value of Iz is nothing but m square by 2. So m square by 2 is nothing but 2 into Ix. Ix. For moment of inertia passing through the plane of the disk and the center of mass of the disk is nothing but a mass square by 4 is equals to Ix. The fourth variation of disk is nothing but, okay, this is the disk. The axis is passing through the plane of the disk and is touching the sides of the disk. Okay, so I is nothing but moment of inertia passing through center of mass plus mass into distance between the axis. Okay, I is equals to 1 by 4 plus 1. What is 1 by 4 plus 1? 5 by 4. 5 by 4 m square. M square. So this is our moment of inertia for wind. Understood the derivation, okay, and the four variations. Okay, if certain variation comes, find the moment of inertia out here. You know how to apply perpendicular acceleration theorem and parallel axis theorem. Okay, so those are elementary in nature. The third thing that we are going to discuss is cylinders. Okay, so cylinders. Now cylinders can be of two types. Okay, hollow cylinder. That means the cylinder, the entire mass of the cylinder is at the surface. Okay, there is nothing inside the cylinder. That means the entire mass of the cylinder is at the surface of the cylinder. Okay, no mass of the cylinder is inside the cylinder. And the second type is solid cylinder. Solid cylinder means the entire mass is distributed throughout the cylinder. Okay, hollow cylinder and solid cylinder. Okay, so the moment of inertia about this axis is same as moment of inertia operating I is equals to m into r square, where m is mass of the cylinder and r is nothing but radius of the cylinder. Whereas for this solid cylinder, okay, moment of inertia is nothing but same as circular disk, m r square by 2. But m is nothing but mass of cylinder and r is nothing but radius of cylinder. Okay, now you can apply parallel axis theorem if they ask you the moment of inertia through the sides of the cylinder. Okay, but you cannot apply perpendicular axis theorem for cylinders. Remember that. Why? Because cylinder is a 3D object. So unlike ring and disk, you cannot apply perpendicular axis theorem in cylinders. Whereas you can apply parallel axis theorem. Okay, they might ask you find the moment of inertia over this axis passing through the side, or find the moment of inertia over this axis passing through the sides. Okay, but the question won't be coming as find the moment of inertia through this axis that is passing through the center. Understood? Now we'll start with rod. So you have finished up two cylinders. Okay, the next moment of inertia we'll discuss is about rod. Okay, so out it. Just wait a minute. Okay, so out here, moment of inertia of a rod. Okay, one thing that you have to understand is, okay, a rod is a 1D object. Okay, so suppose there is a rod of mass m. Okay, the mass of this rod is m, and the length of this rod is l. Okay, what is the moment of inertia of this rod? See, the first thing is the moment of inertia of this rod. Okay, of this rod about the axis passing through the center of the rod. That means if the rod is like this, okay, the axis will pass like this, and the rod rotates somewhat like this. So this axis is nothing but axis passing through the center. So moment of inertia of the rod is nothing but m l square by 12. Where m is mass of the rod, l is nothing but length of the rod or entire length of the rod divided by 12. Okay, let me go to the derivation of this one. Okay, so derivation. How do we derive it? Okay, so this is the axis of the rod and this is the entire rod. I'll just go through the derivation very quickly. So we assume an elemental mass dm out here. Okay, and this delay mass is nothing but of dx length of distance x from the axis. The length of the rod is L. Okay, so half of this portion is nothing but L by 2, the other half is nothing but L by 2. So this portion is nothing but L by 2, this portion is nothing but L by 2. Okay, and moment of inertia is nothing but I, or elemental moment of inertia. What is elemental moment of inertia? Moment of inertia of this specific elemental mass. That means moment of inertia of this much mass only. Okay, about the axis. Of this much mass only about the axis. So moment of inertia of this much mass only about the axis is nothing but how much? dm into distance of this elemental mass from the axis is nothing but x into x square. Now in this parameter, I must convert dm in terms of x or x in terms of dm. Okay, so let me assume the linear density of the entire rod is constant. So let's say the linear density of the rod is rho, okay, or lambda. Lambda is nothing but linear density of the rod or mass of the entire length of the rod divided by total length of the rod. That is nothing but the linear density. Okay, who should be equal to the linear density of this elemental mass? That means dm by dx, isn't it? The rod is made up of uniform material, so the linear density of the entire rod is equal to linear density of this much amount of material. That is what I've written out here. Okay. Now if I take these two terms, m by l is equal to dm by dx, and if I send this dx out here, I can easily say that dm is equals to m by l into dx, isn't it? I have to substitute this dm out here. dm is equals to m by l into dx into x square. And now this became very simple. Moment of inertia is equals to m by l into x square dx, and I have to integrate this. Now my question is, what are the limits of integration? See, limits of integration are nothing but minus L by 2 to plus L by 2. Why? Because out here, the rod goes up to negative L by 2. Out here, you have to integrate from here to here, no? And where is 0? 0 is at the axis or at the center of the rod, isn't it? So minus L by 2 to plus L by 2. Minus L by 2 to plus L by 2. So dI is equals to m by L, which is a constant, x cube by 3, which is nothing but L by 2 to minus L by 2. And when I solve this one, moment of inertia is nothing but m by L into m by 3L. Okay, I've taken this 3 outside the bracket. Okay, into L by 2 whole cube minus of minus L by 2 whole cube, isn't it? And if I solve this one, it is nothing but L cube by 2 cube is nothing but 8 minus of minus L cube by 8, which is nothing but 2L cube by 8. Okay, so moment of inertia of the rod is nothing but m by 3L into 2L cube by 8. And 4 it will get cancelled. I is equals to ml square by 12. Out here L and this L cube would get cancelled to become L square. Understood? So do not get confused about arithmetic. So moment of inertia about a rod passing through the center is nothing but ml square by 12. Okay, ml square by 12. Now there are certain variation of this problem. Variation of this problem is, what are the moment of inertia? What is the moment of inertia passing through the sides? I have already done this question. Okay, but the moment of inertia that is passing through the side is nothing but ml square by 3. I is equals to ml square by 3. And how do I derive this one? We use not perpendicular axis theorem, parallel axis theorem. Okay, where parallel axis theorem states that moment of inertia through this axis, okay, moment of inertia through this axis is equals to moment of inertia passing through the center of mass plus m into r square, where r is the distance between the axis, and the distance between the axis is nothing but L by 2. L by 2 square. So I is equals to ml square by 12 plus ml square by 4, which is nothing but I is equals to ml square by 3. Okay, you can also obtain this formula by integration method. You just have to take the axis out here. Okay, so these are the two variations of the question. Now certain of you might have a question, sir, what about this axis? Okay, axis passing through this. What is the moment of inertia of a rod passing through this axis? Okay, or this axis. The axis is inside the rod. Apply some common sense. Okay, a rod is a 1D object. That means all the masses are towards the axis, isn't it? Or a distance 0 from the axis. That means the entire moment of inertia is 0. No? Rod is a 1D object. This rod out here is a 1D object. Okay. So only axes that are perpendicular to this to the rod will have moment of inertia. Understood? That's it. The next thing that is on our list is rectangular plate. Okay. So start with rectangular plate. Rectangular plate. Okay. A rectangular plate is there. Okay. Of length L and breadth D. Okay, a rectangular plate is there of length L and breadth D. That means our rectangular plate is in this plane. Okay, what is the moment of inertia passing through the center? This is the plane of a rectangular plate. The plate is not like this. Okay, this is the plane of a rectangular plate. What is the moment of inertia passing through one of the sides? Okay, or what is the moment of inertia passing through the center of this rectangular plate? So if I take this axis, okay, moment of inertia passing through this axis is nothing but I is equals to m L square by 12. Okay, m L square by 12. But m is nothing but the mass of the rectangular plate. A rectangular plate is a 2D object. Okay, 2D object. Now you might have some intuition, sir. Isn't this formula ml square by 12 similar to this formula of the rod? Isn't it? This formula of the rod is very similar to this formula of this rectangular plate. Why is that? See, if I take this rectangular plate, no, okay, say suppose this entire rectangular plate is of mass m. Okay, now divide this mass m into very thin sticks. Okay, okay, what is the moment of inertia of each of these thin sticks? Elemental mass into L square by 12, isn't it? And if you add those all moment of inertia, you'll get nothing but m into L square by 12. What I'm trying to say is, suppose take this rod, okay, and divide it into very thin strips, like this, okay, like this, very thin strips. I want to find out the moment of inertia of this rod. The length of the each of the strips is nothing but L. Okay, the mass of each of the element is dm, and the total mass of all the rods is nothing but n. Okay, n. So moment of inertia of all these bodies is nothing but dm into L square by 12. Okay, first rod dm into L square by 12. Second rod is also dm into L square by 12. Third rod is also dm into L square by 12, and so on. And if you take L square by 12 common for all this, you would get dm plus dm2 plus dm3. That means mass of 1 plus mass of 2 plus mass of 3, or dm1 plus dm2 plus dm3. Okay, 1, 2, dm3, and so on, and so on. Okay, and integration of all these masses is nothing but m only. So you get moment of inertia is nothing but ml square by 12. Simple enough. Okay. Similarly, if my axis of the same rectangular plate, okay, this is the same rectangular plate of length L and breadth D. Okay, what about the axis that is passing like this? That means that is cutting B through half. The moment of inertia of this axis is nothing but m B square by 12, isn't it? M B square by 12. So moment of inertia of this axis of the rectangular plate is nothing but ml square by 12. Moment of inertia of this axis, okay, this axis that is cutting the breadth is nothing but mb square by 12. Now what about the moment of inertia, okay, of the same rectangular plate of the axis that is perpendicular to the plate? Perpendicular to the plate means this is the plane of plate and my axis is going like this. Okay, this is the plane of this rectangular plate and my axis is going like this through the center. Okay, so the moment of inertia about this axis is nothing but, or about this axis is nothing but, we can easily apply perpendicular axis theorem. So moment of inertia about this axis is nothing but moment of inertia about length plus moment of inertia about breadth. So moment of inertia about the axis that is passing perpendicular to the plate is nothing but ml square by 12 plus mb square by 12. Okay, similar kind of thing. See, there are certain multiple other variations. The multiple other variations are nothing but, what is the moment of inertia about this axis? It is nothing but ml square by 3. What is the moment of inertia about this axis? It is nothing but mb square by 3. Okay, so what is the moment of inertia that is perpendicular to the plate but passing through one of the vertices? It is nothing but ml square by 3 plus mb square by 3. Understood? Similarly, certain or someone asks what is the moment of inertia about this axis, okay, passing at this point that is inside the plate, passing at this point inside the plate. Okay, how do we solve this kind of problem? Simple, moment of inertia out here. Okay, apply parallel axis theorem plus moment of inertia out here. Out here also you have to apply parallel axis theorem to find out the moment of inertia about this axis, and then apply perpendicular axis theorem on both those bodies to get the moment of inertia about this axis. Understood? It is the same principle by which we get moment of inertia about the vertices. Okay, so how do we get moment of inertia about the vertices? Moment of inertia about this axis, and how do I get moment of inertia about this axis? We apply parallel axis theorem. How do I get moment of inertia about this axis? We also apply parallel axis theorem, and we add those parallel axis theorem to get the moment of inertia about the vertices. No, similar kind of method can be applied to approach moment of inertia about any point inside the rectangular plate. Okay, if the axis is perpendicular. So that's it. Okay, so that there goes our rectangular plate. Now the next part of the problem, okay, rectangular cube. So rectangular cube is nothing, a 3D body. Rectangular cube. This is a 3D body. 3D body means perpendicular axis theorem are not applicable out here. Okay. So suppose, although parallel axis theorem is definitely applicable. So this is a cube. Okay. Let the length of the cube be L, breadth of the cube be B, and height of the cube be H. This is height of the cube. Let's say this is height of the cube. What is the moment of inertia about an axis that is passing through the center of the cube? That means if this is a cube, okay. So suppose there is a cube. Let me show you a cube. Suppose this is a cube. Okay, this is a cube. What is the moment of inertia that is passing through the center? Okay, passing through the center. This axis. Okay, this is the axis of the cube. Fine. So the moment of inertia about this axis should not be or should be is equals to I is equals to m into by 12 L square plus B square. Okay. So how did you get this one? The same way I got this. Not this one. The same way I got this rectangular plate. Okay. I stacked a lots of rod, okay, into the axis and got the moment of inertia of a rectangular plate. Similarly, if I stack a lot of rectangular plate on top of each other, the moment of inertia of this rectangular plate is nothing but ml square by 12 plus mb square by 12. Then I stacked a lot of plates, okay, lots of plates. And if I add the moment of inertia of all these plates about this axis, it is nothing but ml square by 12 plus mb square by 12. Okay, I'm stacking a thin slices of rectangular plate on top of each other till they make up the height h. Understood? Similarly, what is the moment of inertia of the same this rectangular cube of length L, breadth B, and height H about this point? Say about this point. That means now the axis is passing through. See, initially the axis was passing through this point. This was the first thing. Now the axis is passing through this point. Okay, this is nothing but if you tilt it like this becomes another rectangular cube. No, so it is nothing but moment of inertia out here is nothing but m into by 12 into h square plus what is this length? B square. H square plus B square. That means you have to, in the first case, you have to see this face as a rectangular cube. In the second case, you have to see this face as a rectangular cube. Okay. Similarly, if moment of inertia about this face is asked, or about this axis is asked, okay, it is nothing but this is length, this is breadth, and this is height. It is nothing but you have to consider this face, isn't it? The moment of inertia about this axis is nothing but m by 12 into how much? H square plus L square. Okay. So moment of inertia of a rectangular cube is nothing but slices of moment of inertia of rectangular plate stacked on top of each other. Okay. So this is a moment of inertia for a rectangular cube. Now what we have to do is we have to integrate the spherical shell, or now we'll deal with spherical shell. Okay. Spherical shell. Okay. So in your syllabus, whenever spherical shell comes up, be it the chapter of rotational mechanics, be in the chapter of electrostatics. So whenever spherical shell comes up, the method to integrate a spherical shell is always same. Okay. So suppose this is a spherical shell. Okay. This is a spherical shell. Inside the shell, it is nothing there. That means inside the shell is hollow. Okay. So how do I integrate the spherical shell? We divide the shell into number of rings. So this is one ring. Okay. Then another ring. Then another ring. So we divide the shell into number of rings, and then we integrate the ring. Okay. So let's say I taken my element to be this ring. Okay. This is a ring inside the shell. Okay. So if the mass of the entire shell is m, and if I isolate this ring out here, if I isolate this ring out here, okay, let the mass of this ring be dm. Understood? I just took this ring and isolated it out here. I must find out what is the moment of inertia of this spherical shell about this center, passing through the center. Okay, that means if I take this axis and integrate all the rings from top to bottom, okay, I'll get the moment of inertia of this spherical shell, isn't it? Okay. Now the method to integrate this spherical shell is nothing but we have to find out the area of this ring. And how do I find out the area of this ring? Area of this ring is nothing but 2 pi r into this much thickness, isn't it? The circumference of the ring or the perimeter of the ring into this much thickness. So area of this ring that is cut out from the shell is nothing but 2 pi r, 2 pi r, where r is nothing but radius of the ring into this thickness. Okay. Now, how much is this thickness? Okay. To find out this thickness, you have to take the radius of the shell. Okay. Radius of the shell is capital R. Understood this much? This is the radius of the shell, and small r is nothing but the radius of it. Radius of the shell. Okay. Oh, sorry. Radius of the ring will vary as I go from top to bottom. Out here, the radius of the ring would be very small. At the center, the radius of the ring would be very large. Okay. So, how do I find out the relation between this radius of the shell and radius of the ring? If I make an angle out here, theta, can I say radius of the ring or r, radius of the ring is nothing but r sine theta? See, this one, this line, and this line makes a right angle triangle. So r cos theta is nothing but this much, isn't it? And r sine theta is nothing but this much. Okay, so this much length is nothing but r sine theta. So I can easily say out here is nothing but r is equals to radius of the shell into sine theta. Very fine. And thickness is nothing but r into d theta. D theta means we take an elemental angle out here, theta and d theta. This thickness is nothing but radius of the shell into d theta. R d theta is nothing but this thickness of the ring. Okay, understood? So area of the ring is nothing but 2 pi r into thickness. Thickness is nothing but r into d theta. R into d theta. Thickness of the ring is nothing but r into d theta. Okay, and let's substitute this value of small r out here, isn't it? So area of the ring is nothing but 2 pi. What is the value of r? What is the value of small r? R or capital R sine theta. R sine theta into r d theta, which should be equals to 2 pi r square sine theta. 2 pi r square sine theta into d theta. Okay, which is equals to 2 pi r square sine theta d theta. Now my entire portion of the problem is solved. I just have to integrate this ring from top to bottom. And how do I do it? If I take theta out here like this, at the top, when I'm taking this ring, theta is equals to 0, isn't it? And at the bottom, when I'm taking this much ring, theta is nothing but 180 degree or pi radians. Okay. So I must find out the moment of inertia of this shell. Okay. So if I find out the moment of inertia of this ring, okay, of this elemental ring, and add all the moment of inertia of the elemental ring from top to bottom, I'll get the moment of inertia of the shell, isn't it? So moment of inertia of this elemental ring is nothing but mass of this elemental ring, which is nothing but dm, into what is the moment of inertia of a ring? Moment of inertia of a ring is nothing but m r square, or mass into r square. So m into this r square, where r is nothing but r sine theta. R sine theta square. This is nothing but moment of inertia of this elemental ring. Okay, fair and fine. Now somehow I must relate this dm with respect to r and sine theta. And how do I do that? I know that the sphere is made up of uniform material, isn't it? So the density or the surface area density of this entire shell is equals to surface area density of this ring, isn't it? The surface area density, that means the area density of this shell, is equals to area density of this ring, because both are made of the same material, isn't it? So density or areal density is nothing but mass of the shell, the entire mass of the shell, divided by surface area of the shell. Surface area of the shell is nothing but 4 pi r square, which is equals to density or area density of this ring. That means mass of the ring is nothing but dm divided by surface area of this ring. Surface area of this ring is nothing but 2 pi r square sine theta d theta. Area of the ring is nothing but 2 pi r into thickness, and thickness is nothing but r d theta. So 2 pi r into thickness. Thickness is nothing but r d theta. So surface area of the ring is nothing but 2 pi r square sine theta d theta. 2 pi r square sine theta d theta. Now if I take just only these two terms, okay, these two terms, I'll get nothing but m by 4 pi r square is equals to dm by 2 pi r square sine theta into d theta. Okay, so pi and pi r square and r square will get cancelled. 2 would become out 2 out here. So dm is equals to m sine theta d theta by 2. Just send sine theta d theta to the left hand side, isn't it? So dm is equals to this value. Now if I replace dm out here, I'll get moment of inertia is equals to dm. dm is nothing but m sine theta d theta by 2 into r sine theta whole square, isn't it? Di is equals to m by 2 into r square into r square, where r is nothing but the radius of cell, into sine cube theta d theta. Sine cube theta because sine square theta into sine theta is nothing but sine cube theta into d theta. Okay. Now if I integrate sine cube theta d theta from pi or from 0 to pi, I'll get the moment of inertia. Sorry, this is not d theta, this is di. Okay, I'll get the entire moment of inertia of this shell. Understood? So if I integrate this parameter, I'll get the moment of inertia of this shell. So if I now just solve this integral, okay, I'll get the moment of inertia of a spherical shell. Okay. Now to solve this integral, you need to remember a certain mathematical formula, and that formula is sine 3 theta is equals to 3 sine theta minus 4 sine cube theta. Okay, sir, how do we know this formula? Okay, or how did I derive this formula? See, first I'll use this formula to find out the value of sine cube theta, and then I'll integrate the shell and find out the moment of inertia of a spherical shell. And at the end, I'll give you the derivation of this formula. How is sine theta is equals to 3 sine theta minus 4 sine cube theta. Understood the order by which I'm going? First, from this equation, let us just assume that there is an equation that says this. From this equation, I'm going to derive the formula for sine cube theta. This sine cube theta would be replaced out here. Okay. Then I'll integrate the problem, or I'll integrate the solution, and then I'll find out the moment of inertia. And then at the end, I'll explain how this sine cube theta or how this relation is being formed. Understood the order? Okay. So from this equation, suppose I already know this equation is in effect, or this there is a equation that says sine 3 theta is equals to 3 sine theta minus cosine cube theta. So from this equation, I can easily say that cosine cube theta is equals to 3 sine theta minus sine 3 theta, isn't it? Or sine cube theta is equals to 3 sine theta by 4, or 3 by 4 sine theta minus sine 3 theta by 4. Understood up till here? Okay, so sine cube theta is nothing but 3 by 4 sine theta minus sine 3 theta by 4. Okay, now just substitute the value of sine cube theta out here in this equation. This equation says nothing but moment of inertia is nothing but m by 2 r square. So out here, just let me just erase the remaining portion. Okay, I'll just erase the remaining portion, that means portion that is not required out here. Okay, so let me erase these all things. I must only solve this one, no? This is my parameter of interest. Okay, this is my parameter of interest, and the limits of integral are from 0 to pi. Okay, so sine cube theta is nothing but 3 by 4 sine theta minus sine 3 theta by 4. So di is equals to m by 2 r square integral of 0 to pi 3 by 4 sine theta minus sine 3 theta by 4, isn't it? Into d theta. This out here is the value of sine cube theta, isn't it? Or moment of inertia di is equals to m by 2 r square. Can I take this 4 or constant 4 outside the bracket? Of course. So into 4. So if I take into 4 out here, this 4 and this 4 will come outside. Very fine. So it is nothing but m by, or mr square by 8. Mr square by 8 into how much? 3 sine theta d theta from 0 to pi minus sine 3 theta d theta from 0 to pi. Okay, I'm just separating out the integral. Now if I integrate this one, 3 sine theta is nothing but minus of 3 cos theta from 0 to pi. Okay, if I take the minus outside, okay, I'm just taking the minus outside the bracket. You can take the constant term of integration outside the bracket. Okay, you can take minus 3 outside. 3 is also a constant, no? So I'm taking minus 3 outside the bracket. Okay, so it will become nothing but minus 3 cos of pi. Cos of 180 is nothing but minus 1, minus 1, minus of cos of 0. Cos of 0 is nothing but 1. So minus 1. So it will become minus 3 into minus 2. It is nothing but 6. Fair and fine. Out here, if I integrate sine 3 theta d theta, it is nothing but minus of cos 3 theta by 3, isn't it? Minus of cos 3 theta by 3 from 0 to pi. Similarly, if I take out the constant outside, minus 1 by 3 cos 3 theta from 0 to pi. So if you put out the value of pi out here in the value of theta, it will be cos 3 pi. Cos 3 pi is nothing but 180, 360, 570, isn't it? Yeah. So cos 3 pi is nothing but plus, minus, plus. Cos 3 pi is nothing but 1, isn't it? So cos 3 pi, so minus 1 by 3, okay? Let me check, okay? 0, 5, okay? 2 pi, 2 pi, 3 pi. Achha, cos 3 pi is minus 1. I made a mistake out here. Cos 3 pi is minus 1. From out here to out here, pi. From out here to out here also, pi. Okay, from out here to out here also, pi. Okay, so cos 3 pi is minus 1. Minus of cos 0 is nothing but 1. 3 into 0 is nothing but 0, and cos of 0 is nothing but 1. So out here it is nothing but minus 1 by 3 into minus 2. It is nothing but minus, not minus, 2 by 3. Okay, so I'll delete this. So moment of inertia out here is nothing but mr square by 8 into 6 minus 2 by 3. See out here, moment of inertia is nothing but mr square by 8 minus this value, and this value is nothing but 6 minus this value. This value is nothing but 2 by 3. So if I integrate it, moment of inertia of the entire spherical shell is nothing but mr square by 8. 6 minus 2 by 3 is nothing but 18. If I take the LCM, 6 is 18 minus 2 by 3. So 18 minus 2 is nothing but 16. 16 by 3. 16 by 3. 8, 2 is a 16. Okay. So 2 by 3 mr square. So moment of inertia of a spherical shell is nothing but 2 by 3 mr square. The only physics part you need to remember is the derivation. Okay, I took an elemental ring and I integrated those elemental ring from top to bottom. Okay, and how did I take the elemental ring? I took the elemental ring 2 pi r, area of the ring, okay, is equals to perimeter of the ring into this much thickness, and this much thickness is nothing but r d theta. Then I took planar density or areal density is equals to mass by total surface area of the ring is equals to elemental mass of the ring divided by total surface area of the ring, isn't it? And then I integrated the moment of inertia of the entire ring from top to bottom. Okay, and while integrating there was a mathematical bootleg of sine cube theta, okay, that I told you is this value, okay, and this is the value of sine cube theta. Now replacing or substituting the value of sine cube theta out here like this, I obtained my answer to be this one, 2 by 3 mr square. So remember one thing, okay, moment of inertia of a spherical shell is equals to 2 by 3 mr square. Okay, and to derive this moment of inertia, I use the moment of inertia of an elemental ring. Okay, so some of you might, so in other books, in all the books it is written mr square. So you might get the idea that the derivation of this shell is done by using elemental or elemental masses. It's not that. The moment of inertia of this shell is derived by using elemental rings. Why? And why I'm repeating that is, while deriving moment of inertia of a sphere or solid sphere, okay, you'll understand that you have to take elemental shells out there. Out here I took elemental rings, no? Okay, by integrating all the elemental rings, I derive the moment of inertia of the shell. But while deriving the sphere or solid sphere, you have to take elemental shells. And by integrating elemental shells, you get the moment of inertia of a solid sphere. Or you can also take elemental disk. Okay, and by integrating elemental disk, solid disk, not hollow disk, solid disk. And by integrating solid disk, you get the moment of inertia of a solid sphere. Okay, so you always have to integrate the moment of inertia of basic shapes. The basic shape out here is the ring out here. And the moment of inertia is nothing but 2 by 3 mr square. Now let's go to the mathematical part of the problem. Okay, sir, how did you obtain this one? This one will be taught in your mathematics. Then also I'm going over a little bit quickly. Okay, see okay. Sine cube x, or sorry, sine 3x. Okay, we will only use two formula for mathematics. Okay, or two theorems of mathematics. The first theorem is sine a plus b. Okay, or a plus minus b is equals to sine a cos b plus minus cos a sine b. What I mean is sine a plus b is equals to sine a cos b plus cos a sine b, and sine a minus b is equals to sine a cos b minus cos a sine b. And the second formula is that I'm using is cos a plus b, or cos a plus minus b is equals to cos a cos b minus plus sin a sin b. What I mean out here is cos a plus b is equals to cos a cos b minus sin a sin b, and cos a minus b is nothing but cos a cos b plus sin a sin b. That means if you use plus out here, you'll use minus out here. If you use minus out here, you'll use plus out here. These are the two mathematical theorems that I'm going to use, okay, for the derivation. Mathematical theorem that you're already supposed to know. Trigonometric theorems. Okay. Okay. Now sine 3x. This sine 3x can be written as sine x plus 2x, isn't it? X plus 2x is equal to 3x. Okay. Now if I apply this formula, sine x plus 2x out here, sine a, this one, I'll get this one, sine x cos 2x plus cos x sine 2x, isn't it? I just apply this formula out here, sine x plus 2x. Now my entire target out here is convert every parameter out here in terms of sine. Okay. See out here. By using this formula, I got this parameter, isn't it? And the problem out here is cos 2x. Okay. How do I derive cos 2x? I use the same formula out here. Cos 2x can be written as cos x plus cos x, sorry, cos x plus x. So cos x, and minus sin x, sin x. So cos square x minus sin square x. So cos 2x can be written as cos square x minus sin square x. And this is derived by using this formula. Okay. So sin x cos 2x, sin x cos 2x. This entire thing is cos 2x plus cos x. This out here is nothing but cos x into sin 2x. See, sin 2x can also be written by this formula. Sin x plus x is nothing but sin x cos x plus cos x sin x is nothing but 2 into sin x cos x, isn't it? So 2 sin x cos x is nothing but sin 2x. If you use sin x plus x out here, okay, so you'll get sin 2x is equals to 2 sin x cos x. And if you use cos x plus x out here, you'll get cos 2x is equals to cos square x minus sin square x. Understood? So I replace the cos 2x out here and sin 2x out here. Okay, fair and fine. Now I simply, what I did out here in the second step, this cos square x is written as 1 minus sin square x. And you might ask, sir, why is that? How? You already know from trigonometric theorem. Sin square x plus cos square x is equals to 1, isn't it? So can I write cos square x is equals to 1 minus sin square x, isn't it? Okay, so this cos square x is written out here as 1 minus sin square x, isn't it? And sin square x was already out there, plus 2 sin x cos x means I multiply this entire thing inside the bracket. So 2 sin x into cos square x. This cos x and this cos x are multiplied. Understood up till here? Now minus sin square x and minus sin square x. In the third step, sin x 1 minus 2 sin square x. This out here is added. Okay, plus 2 sin x cos cube x. This is left as it is. Okay. Now in the fourth step, I apply this formula. Okay, what I'm trying to do is, see, in the first, this parameter, sin x into 1 minus 2 sin square x. In this parameter, I simply multiply sin x inside the bracket. Sin x into 1 is nothing but sin x. Sin x into 2 sin square x is nothing but minus 2 sin cube x. Okay. In the second part, this cos square x is again expanded in the form of 1 minus sin square x. Understood this one? Okay. So this cos square x was again expanded out here. Now sin x minus 2 sin cube x, same as before. These two terms are same as before. This term is also same as before. Okay. Now minus 2 sin cube x. Okay. What I did out here is I multiplied this term, this entire term inside the bracket. That means 2 sin x is multiplied by 1 minus sin square x. This term, okay, is nothing but this entire term. So it is nothing but 2 sin x into 1 is nothing but 2 sin x minus 2 sin x into sin square x is nothing but minus 2 sin cube x. Okay. And in the fourth step is nothing but I added the similar terms. Plus 2 sin x and plus sin x. It is nothing but 3 sin x minus 2 sin cube x, and minus 2 sin cube x is nothing but minus 4 sin cube x. And we get the formula sin 3x. Okay. Sin 3x is equal to 3 sin x minus 4 sin cube x. Okay. Or sin 3 theta is equal to 3 sin theta minus 4 sin cube theta. And by using this, to obtain the moment of inertia of a spherical shell. Okay. So there is the spherical shell. Now the fifth path of moment of inertia is nothing but spherical shell. Spherical sphere. The difference between shell and sphere is nothing but shell is hollow inside, whereas sphere is completely filled. Okay, spherical sphere. This is a spherical sphere of radius r. Okay, and to integrate spherical sphere, I must take elemental shells. Elemental shells inside the sphere. Okay, so let the thickness of this, let the radius of the shell be r. Let the thickness of this shell be dr. Okay, so my first question is, what is the volume of the shell? So volume of the shell is nothing but surface area of the shell into thickness, isn't it? Volume is equals to surface area into thickness. Area is equals to length or perimeter into thickness. Okay, so volume of the shell is nothing but surface area of the shell into thickness of the shell. And what is surface area of the shell? Surface area of the shell is given by 4 pi r square, isn't it? And the thickness of the shell is given as dr. Okay, so volume of the shell is nothing but 4 pi r square dr. Okay, and to find out the moment of inertia of this shell about the axis passing through center. Okay, so I must find out the moment of inertia of this spherical shell that is passing through center, isn't it? And what is the moment of inertia of this spherical shell? The moment of inertia of this spherical shell is nothing but, I have obtained out before, or obtained this answer before, is nothing but 2 by 3 mass of the shell into radius of the shell square. So moment of inertia of this spherical shell is nothing but 2 by 3, or moment of inertia of this spherical shell is nothing but 2 by 3 into mass of the shell. Mass of the shell is nothing but dm. And if I integrate the entire shells, I'll get the mass of the solid sphere, which is nothing but m. So 2 by 3 dm. dm is nothing but mass of the shell into r square, where r is nothing but radius of the shell. Fair and fine. Now somehow I must relate dm and r. And to relate that, I use volumetric density. So volume of the, or density of the entire sphere is equal to density of the shell, because both are made of the same material. And what is density of the sphere? Mass of the entire sphere divided by volume of the entire sphere, 4 by 3 pi r cube, is equals to mass of the shell divided by volume of the shell. What is volume of the shell? 4 pi r square dr. Volume of the shell is nothing but 4 pi r square dr. So out here, 4 pi, 4 pi, 4 pi get cancelled. Okay, okay. dm is equals to 3m by r cube. Okay, these three would go upward, 3m by r cube. And this r square dr would go to the left into r square dr. Remember, this r is the radius of the shell or elemental shell, whereas capital R is nothing but radius of the solid sphere. Okay, solid sphere is nothing but completely filled inside. That means the entirety of the shell is filled. Okay, it is not hollow. Shells out here are hollow inside. That means nothing is there inside. All the masses are situated at the surface. Whereas in sphere, all the masses are distributed uniformly throughout the volume. Understood the difference between shell and sphere? Now, to find out the moment of inertia of a spherical shell, I use elemental shell. Okay. So from this equation, I get di is equals to 2 by 3. What is the value of dm? dm is nothing but 3 into mass by r cube into r square dr. Okay, this is nothing but dm into r square. This r square also have to be bought, no? So 3 and 3 would get cancelled. So di is nothing but 2m by r cube into r square, r to the power 4 dr. And the limits of integration are from 0 to capital R, isn't it? 0 to capital R. So di is equals to 2m by r cube from r to the power 5 by 5 from 0 to capital R. di is equals to 2m by r cube into r to the power 5 by 5 minus 0, or moment of inertia of the entire spherical sphere is nothing but 2 by 5 m r square. Okay, okay. The variation in the variation in spheres and shell is, there are two types of variation in shells and sphere. Okay, the first variation is very simple. They'll use parallel axis theorem. Find out the moment of inertia passing through this axis, or find out the moment of inertia passing through this axis. Okay, so you can easily apply parallel axis theorem and find out what is the moment of inertia through one of the sides. The second variation, okay, the second variation is very important. That is the purpose of why I'm showing you the integration out here. Okay, the entire purpose of showing you the integration is in the exam. Okay, they might not give you the full find out the moment of inertia of a spherical shape. Okay, they might give you find out the moment of inertia through a hemisphere passing through this axis. What will you do? Okay, so you must take a note of how the elements are integrated. Okay, so even for hemisphere or hemispherical shell, you have to take the same type of integration, no? Or you have to take the same type of element, isn't it? The element won't be any different. Understood? So the purpose of showing you the derivation is nothing but for hemisphere, okay, for quarter of a sphere, or for a spherical arc, okay, you must be able to find out the moment of inertia. Okay, so this was the moment of inertia of a spherical shell. Okay, similarly out here the variation would be moment of inertia through the sides. Apply parallel axis theorem. Okay, moment of inertia of a hemisphere. Understood? Apply the same methods of integration. Okay, and you can use. I'll teach you some more tricks to find out hemispheres and this kind of thing. Okay, but for now, just find out moment of inertia, or just apply integration to find out moment of inertia of spherical shape. That means just note how am I integrating. Okay, the method of integration. For spheres, I'm taking elemental shells. For shells, I'm taking elemental rings. Okay, just note down the method of integration, not the mathematical formula. Means the method of how I'm taking the elements out there. Okay, the same methods will be applicable for half or quarter size shells and spheres. Okay, that's it. Now what we'll do is we'll find out the moment of inertia of a cone. Okay, so cone out here. Okay, cone, let there be a solid cone. That means the cone is filled. Okay, the base of radius of the cone is r, and the height of the cone is h. Okay, we have to find out the moment of inertia of this cone about this axis. Fair and fine. And the cone angle is nothing but given by theta, or semicone angle is given by theta. Okay, how do I find out the moment of inertia of this cone? And what are the elements, or how do I take the elements? See, while dealing with cone, the element is nothing but a circular disc. Okay, circular disc of thickness dx. Let the radius of the circular disc outside be r. Okay, so my first question is, what is the moment of inertia of the circular disc about this axis? The moment of inertia of the circular disc about this axis is nothing but elemental mass of the disc, isn't it, into r square, where r is nothing but the radius of disc. Okay, elemental moment of inertia of this entire circular disc, of this elemental circular disc, is nothing but elemental mass of the disc into r square. This much is done. Okay, now somehow if you see a problem, somehow if I, as I integrate from top to bottom, no, the radius of the disc is variable, or the radius of this disc keeps on changing. So somehow I have to take the parameter, or somehow I have to take this parameter of r and substitute out here. Now how do I figure out by which relation the radius of the disc keeps changing? Simply just take the distance of the disc from the top. Okay, let the distance of the disc from the top be x. Okay, that means my element is situated at x distance from the top. Okay, and now if I see this angle, can I say tan theta is equals to r perpendicular by x? Tan theta is nothing but perpendicular by base. So perpendicular divided by base. So tan theta is nothing but r by x. R by x, which is also equals to this radius of the base of the cone divided by height of the cone, isn't it? Is equals to r by h. So from this relation we get r is equals to r by h into x. Now if I substitute this value of r out here, what do I get? Element moment of inertia of the elemental disk is nothing but dm into r by h into x square. This is solved. Now I have to find out the relation between dm, the elemental mass, and x. Okay, so can I say the density of this entire cone is equal to density of this elemental disk? So volumetric density is equals to nothing but density of the cone. It is nothing but mass of the cone divided by volume of the cone. Volume of cone is nothing but pi r square h, isn't it? Volume of the cone is nothing but pi r square h. Okay, okay, which is equals to elemental mass of the disk. Elemental mass of this disk, which is nothing but dm out here, elemental mass of the disk, divided by volume of the disk. Volume of the disk is nothing but pi r square, area of the disk into dx, height. So volume of the disk is nothing but pi r square into h. Okay, pi r square, or area of the disk into height. Out here height of this elemental disk is nothing but dx. See, dx is nothing but the thickness of the disk. dx is nothing but the thickness of the disk. R we have found out is nothing but capital R by h into x. So if I substitute all this, m is equals to 1 by 3 pi r square h is equals to dm divided by pi into r by h into x whole square into dx. Okay, this r square is substituted as r by h into x whole square. Okay, pi out here and pi out here will get cancelled. R square and r square is getting cancelled. Okay, so I'll get 3m by h. I'm taking these three to the top. Okay, 3m by h is equals to dm by x square dx by h square, isn't it? And this h square I'm sending it to the top. And if I send this h square to the left hand side, this will become h cube. Okay, so let me modify this equation neat and clean. Fair and fine. Or elemental mass is nothing but 3m by h cube into x square dx. So if I substitute the elemental mass out here, what do I get? Moment of inertia is nothing but elemental mass 3 mass of the whole cone divided by h cube into x square dx into r by h x whole square. Now if I open up the square, di is equals to 3m by h cube into x square dx into r square by h square into x square, isn't it? Now if I just solve this problem, is equals to 3m by h cube and h square becomes h to the power 5, x square and x square becomes x to the power 4, and this r square will go out here and become capital R square into dx, isn't it? Or di is nothing but 3m r square divided by h to the power 5 x to the power 4 dx, isn't it? Okay, x to the power 4 dx. Now the limits of integration are nothing but from 0 to h height. I've taken my origin out, so from 0 to height h. So from 0 to height h. So moment of inertia is nothing but 3m r square by h to the power 5 into what is the integration of x to the power 4 dx? X to the power 5 by 5 from 0 to h. So now if I solve this, I'll get moment of inertia is equals to 3m r square by 5, because h to the power 5 out here and h to the power 5 out here would get cancelled. So moment of inertia of a cone is nothing but 3m r square by 5. Okay, just remember how I take the element and I integrate it. Okay, those two things are important out here. So we are done with cone. Okay, now before discussing trapezoid, we will first solve few problems. Okay, so see this problem. Calculate the moment of inertia of a copper uniform disc relative to a symmetric axis perpendicular to the plane of the disc. If the thickness of the disc is equal to 2 mm and its radius is equal to 100 mm. That means out here, I'm doing part A of the question. Okay, this is a uniform copper disc. The radius of the disc is nothing but how much? 0.1 meter. 0.1 meter. Okay, and this copper disc, okay, the thickness, okay, see the copper disc is kept in this plane. The thickness of the disc is given as 2 millimeter out here. Okay, 2 millimeter. We have to find out the moment of inertia. So what is the moment of inertia of a circular disc? The moment of inertia of a circular disc is nothing but how much? This was ring, this was disc. Moment of inertia of a circular disc is nothing but m r square by 2 through the center, isn't it? So moment of inertia is nothing but m into r square by 2. Fine. Okay. In this question, however, instead of using m, okay, or instead of using the mass of this disc, which is m, I want to substitute this variable m out here, in terms of density and volume. Why? Because there is no parameter of mass given out here. No, there is no parameter of mass given out here. Although I do know that the density of copper to be something. The density of copper is always constant. Doesn't matter the volume of the copper or the shape of the copper. The density of copper will always remain constant. So in this question, instead of using mass, they are asking us to use the value of density. Okay, in terms of density. In terms of density. Okay. Now, what is the relation between mass and density? Mass is equals to density into volume, or volume is equals to mass by, density is equals to mass by volume. So if I just replace this mass out here in this parameter, moment of inertia is nothing but density of the copper disc into volume of the copper disc into r square by 2. Now, what is the volume of this copper disc? Okay, it is nothing but area into thickness. See, if this was a copper disc, okay, the radius of the copper disc was nothing but how much? 0.1 meter, and the thickness of the copper disc is nothing but given in the question as 2 millimeter or 0.002 meter. Okay, volume is nothing but pi r square h, where h is nothing but the thickness out here, isn't it? R is nothing but the radius, r is nothing but the radius out here. So moment of inertia of the circular disc is nothing but density of copper into volume pi r square h into r square divided by 2. If I simplify this one, moment of inertia of a copper disc is nothing but density into pi h r to the power 4 by 2. Okay, and one more thing. Okay, just keep it as a note in your brain. Okay, instead of using volumetric density, the density that I have used out here is volumetric density, no? So instead of using volumetric density, if in the question this planar density or area density, that means mass divided by area. Okay, if moment of inertia is given in terms of areal density, okay, means surface area or planar density, that kind of moment of inertia is also called area moment of inertia. Okay, just remember this. It will be helpful in your further studies. Not right now, but in upcoming when you're studying engineering, there will come a term called planar moment of inertia or area moment of inertia. It is nothing but the density or moment of inertia in terms of density, in terms of planar density. The same moment of inertia when described in terms of planar density or area density is nothing but area moment of inertia. Okay, so that was it. Okay, there are some modification to that definition, but that is the gist of it. So part A of the question was nothing but density of the disk, rho into pi into h into r to the power 4 by 2. Now part B of the question. Part B of the question is nothing but solid cone. Okay, uniform solid cone, mass is equals to m, base radius is equals to r. Okay, what is the moment of inertia of a solid cone? Let's see. Moment of inertia of a solid cone is nothing but how much? How much is the moment of inertia of a solid cone? dm. I is equals to 3 by 5 mr square. So moment of inertia of a solid cone is nothing but 3 by 5 mr square. I have already done this in the classes or in the lecture. Okay, just rewind the lecture and see. I have done this one. 3 by 5 mr square. So moment of inertia of a cone is equals to 3 by 5 m r square. Fair and fine. So that there goes our question number 239. Okay,